Hello, everybody. This is Kiran Kumar Challa. I'll be presenting the paper titled Dynamic State and Parameter Estimation of Synchronous Generator from Digital Relay Records. This paper is co-authored by Dr. Gurunath Gurrala. We both are from the Department of Electrical Engineering, Indian Institute of Science, India. So the presentation will be followed in this way. I'll start with the motivation and objective of our work. And I'll explain how we have done the parameter estimation using the digital protective relay records and validation of our results. I'll discuss the conclusions and references. To start with the motivation, you can see in this slide that in 1996, when we have experienced a major collapse in WCC, the recorded waveforms have actually got grid collapse, but the simulation models have predicted a well-damped or the sustained oscillations in the system. There is a discrepancy between the records and the simulated data. Later, even in 2010, due to a tie line loss, in case of this disturbance again, the recorded data shows that there are damped oscillations, but the simulation shows that there are not even significant oscillations. The system is well behaving. Similar kind of discrepancies are observed in 2010 is the case of generator trip, and your frequencies with the simulation data as well as the recorded data doesn't match. The same is the case in 2011. These are the kind of cases the power system engineers have been observing in the grid, and that's where it was made mandatory, especially in North America, that utilities means the power generation companies are mandated to supply the generator data, dynamic data, and they also need to update this data every 5 years by validating the data that they have. And similar kind of exercise also started in India, the country where we are from. The National Thermal Power System Corporation actually made it as a starting point to estimate the parameters of a couple of generators in India. So they started this practice. So in order to actually understand whenever you have a disturbance and you wanted to predict whether it is going to lead to a blackout or what kind of consequences are we going to get, we definitely need the parameters or the dynamic data of a generator. And if you try to look at how this dynamic generator data is obtained in various cases, the majority of the conditions, there is a online parameter estimation using the phasor measurement unit data. And in this case of online parameter estimation, we'll be just taking the data from the terminals of a synchronous generator using the phasor measurement units. And this phasor measurement units gives us the 4 parameters majorly, that is real power, reactive power, voltage, and phase angle. Now, in the most of the estimation techniques, people started taking any 2 of these variables as inputs and try to validate the system data to match the remaining 2 variables as the outputs. So if you take real and reactive power as an input, then you'll be considering voltage and theta as output. And if you're taking the voltage and phase angle as an input, then you have to take the real and reactive power as an output. This is a major problem formulation that has been there in the parameter estimation or model validation. And the other aspect of the problem is that people started using the digital fault recorders data, DFR data. Whereas in case of DFR data, it is not that you have only terminal recordings, you will also get the field parameters. That means the field voltage and field current as an additional measurements you have. And then the same procedure is followed in order to estimate the parameters. But here, the problem with these two is that PMUs, especially in a country like India, we don't have PMUs at every node or every substation. And DFRs also don't record this data in all the plants. So now, if you wanted to get the dynamic data of a plant where you don't have PMUs and you don't have a DFR recording the data, how to handle that? That's where we have come up with estimation of this data using digital protective relay records, because this relay is there for every particular generator. So when you have taken a generator and PMU or DFR data, try to compare what are the differences between these two. This PMU or DFR data is more or less available at a substation level. So it gives you the aggregate model of the entire power plant. And In some of the cases, this PMU or DFR may or may not be available. But if you look at the DPR, protective relays, are there for the individual generators so that you'll be able to get the generator parameters individually. And you definitely have this DPR and you don't have a question of not having it. But the issue with the DPR data is it records data for a shorter duration. Of course, there are advanced DPRs which will record the data for longer, but DPRs are already there in the majority of the plants which are recording the data for 3 to 5 seconds as per our survey from the different power plants. So the sampling rate of this was also less compared to DFR, of course, much high compared to the PMBs. So our objective of the problem is when you don't have the availability of PMUs or DPRs, it is better to estimate the data of the dynamics plant using the protective relays. But the problem with this is the recorded data is only of the 3 seconds length, in which case you have 1 second pre-fall data and 2 seconds post-fall data, and the sampling rate is 1 kilohertz. In order to achieve the estimation within this 3 seconds recorded length, we have gone for the constrained iterative unscented Kalman filter based estimation. And also for the simple calculations and the accurate estimation of the states and parameters, we have opted for the Adomian decomposition method for the differential equation solutions. So the proposed approach has been validated using the VEC 3 machine 9 per system data. Now, at this stage, if you try to look at what is this unscented transform, of course, most of you might be well aware that this unscented transform is based on the idea that it is better to approximate the probability distribution than the random nonlinear functions. So in case of unscented transformations, we'll be having the statistics of the this is actually meant for the getting the statistics of the random variables which undergoes through the nonlinear transformation. So if you just look at the actual or the fundamental methods like particle filters, where you will be taking the vast range of samples which will go through the same nonlinear transformation, but the output covariance and the mean may not be lying within the specified limit. And the second case, the example with the extended Kalman filter, where you approximate the nonlinear function, then you will see that your output mean as well as the covariance will not be within the specified bounds. And if you look at the unscented transform, where your sigma points are strategically chosen using the specific mean and the covariance so that your output will have the mean as well as the covariance close to their true mean and covariance. And this is actually the basic way where the equation shows that you will be generating your sigma points based on the covariance matrix, and then those sigma points are transformed onto the output. Every sigma point will be having the corresponding output, and then you will get your output mean and output covariance, how in the figure they are matched. So this is what is the unscented transform, and this is what is used in the unscented Kalman filter. So what we do in this unscented Kalman filter, we'll start with the initial state. That's an approximation. How best you approximate is also the important thing. And then you will be having the state covariance matrix, how this initial state will be different from your actual state. And using these two, we will be generating the sigma points of the states based on the previous expressions I have given. And then we will also get every sigma point corresponding measurement point in the second step, and we will get the predicted state as well as the predicted measurements. So then this predicted state and predicted measurements will be used to get the measurement covariance and cross covariance, and then these measurement covariance and cross covariance matrices are used to get the Kalman filter gain, and they will give us the state estimate and the state covariance matrix. Again, this is actually for a particular time step, and for the next time step, if you wanted to have the state estimate or the predicted state, then we'll use our dynamic equations in the time update to get the sigma points and then the corresponding covariance. So how this is mathematically done is given as a each step here. The sigma point selection and then the mean calculation is as described in the unscented filter, and each sigma point corresponding output will be calculated, and we will get the weighted mean of the measurements and the weighted mean of the sigma points. And these two, weighted mean and the sigma points, and weighted measurement, weighted average measurement, and the sigma points are used to get the output covariance and cross covariance matrices. So this output covariance and cross covariance matrices will give us the Kalman gain. And based on the Kalman gain, we'll be able to get our predicted state and the covariance matrices. And this is one step. And if you wanted to go for the time update, we'll again, based on this particular state, predicted state, we will try to again use the covariance that we got in the previous stage to get the sigma points. And all the sigma points are transformed down to the next time step using the dynamic equations of the power plant model. Here we have used the 1.1 standard IEEE synchronous generator model, but this is where the Adomian decomposition based synchronous machine equations are taken from the specified reference, and they are used to basically get the time update for the synchronous machine equations. And then after getting all the data points, again, the weighted mean will give us the state predicted state and the state covariance matrices. And this is the basic unscented Kalman filter. And the simple difference between the constrained iterative unscented Kalman filter and unscented Kalman filter is that this measurement update is repeated for the multiple number of times in order to use the single data points for the number of times. And again, at every point when we get our state estimate, we will try to limit that state within its upper and lower limits. If it is exceeding the maximum value, we will restrict it to the maximum. If it is going below the minimum value, we'll restrict it to the minimum. So that's how we'll applying the constraints and as well as iterate it for multiple times in the measurement update itself. So this is what is the CAUKF. And now in order to get the DPR data, we have actually surveyed DPR recordings from the various plants and got to understand that these DPRs are of this 3 seconds data, and there will be 1 second pre-fall data and 2 seconds post-fall data. The same kind of data with 1 kilohertz sampling has been generated using RK4 method in the MATLAB simulations. And then we have taken the corresponding PQV theta from the simulated data, and we tried to use this PQV theta for the parameter estimation using our CAUKF. So the states are chosen like this. These are the states of the synchronous machine, and the parameters to be estimated are represented by phi. And we will be forming augmented state matrix using the states to be predicted as well as the parameters to be predicted. And our inputs are voltages and phase angles, and outputs are considered as P and Q. And while initializing the states, we have taken the parameters as the average of minimum and maximum limits of every parameter given in our standard reference power system stability by Kondur. And also the covariance matrix is given as follows. And using this data, we have estimated the parameters of the generator, and you can see that this CAUKF is performing better and trying to estimate the parameters of the synchronous generator to the better accuracy. And you can see that these are the actual values and estimated values, and the corresponding differences are given. And the major problem that we have faced is actually in the estimation, getting the covariance matrix, but that we are actually still working on to figure out the better covariance matrix. Yeah, so used state estimation, parameters estimated are used to basically get the state estimation, and you can see that the majority of the states are well estimated except the PM and EFD, where we have not considered the dynamics of the governor turbine and the field. If we consider that, then we can actually reduce the errors in those two states also. And again, the parameters estimated are used to get the eigenvalue analysis of the synchronous generator, and you can see that the critical PE as well as XL are well approximated, estimated using the estimated parameters. So we'd like to conclude that. So as a contribution of our work, we have estimated the parameters using the digital protective relay records and selected a CAUKF method in order to achieve the target of estimating parameters in 3 seconds. And for the better accuracy, we have used Adomian decomposition method and validated it using VEC3 machine 9 bus system data. These are the references, and thank you.
Thank you very much. So I don't see yet. I don't see yet any questions in Q&A. So if any of you have, any of attendees have questions, please put them in. You can also raise your hand and then I can probably allow you to speak. So meantime, maybe I'll ask first question. If I got you right, so you've been analyzing historical data. Do you think your method can be promoted to real-time method?
Yeah, we are working on that, sir. Actually, this has been done as a part of applying it to the real-time data.
Okay, good to hear that. And also, you didn't compare with any alternatives. And I wonder why. So you basically compare it with the ground truth, which is good, but there are probably, and certainly there are other methods. So what do you say about that?
Basically, we try to estimate that using UKF, basic unscented Kalman filter, and then we have gone for this constraint iterative unscented Kalman filter in order to achieve that convergence within the stipulated time of 3 seconds. I have shown the results for the UKF method as well as the CA UKF method.
I see. So that's you consider as a comparison. That's fair answer. Yeah. Also, can you maybe comment on what kind of perturbations did you study? So is it well faults of this or that type, or I mean, so what were dynamical data?
Yeah, at this date, it is a 3-phase fault at generator terminals for a 3 cycles of duration.
Okay, thank you. So I think we have 2 questions, and yeah, so first from Hussein, and you can probably see them in Q&A, but let me read them. What is advantage of Kalman filter specifically when we use the data of relay?
Yeah, so the thing is that when we use the Kalman filter, this is well used in the parameter estimation, and the problem is slightly similar to the PMU and DFR data, but that is why we have actually first gone for the Kalman filter and thought that it will be able to give us a solution. But the issue that we faced is when we have gone for the basic UKF method, it was not giving us a solution because the data record we have is only for 3 seconds. In case of PMUs, we'll have a streaming data. So that's when we have gone for using every data point for the multiple times so that you will have a convergence. And that's why we have gone for this constraint iterative Kalman filter. So that's the difference between having your PMU and DFR and relay data. I hope that answers the first question, sir. And
I also hope so. Well, we have one more question, so maybe we'll go to that, and that will be the last one. From Andrei Gorbunov.
Yes, sir.
Are
So
there
is there
any issues? Yeah, go ahead.
Yeah, is there any issue regarding the relays don't have time synchronization? I would like to mention that this is not used for any online control. This problem is meant for providing dynamic data for the control centers for the estimation in the future. Like every plant will have the data, and the generator plants are in US, not actually in India right now. They are made mandatory to submit the dynamic data or update it for every 5 years. So this is an offline problem. So when it is made offline, then we don't have an issue of time synchronization. But definitely when we are using it for the online control, or we have something like WAM based PSS design and all that, in that case, this is not going to help us.
Okay, Kiran, thanks a lot. And your time is up. Good timing.